So continuing on, the next thing that we're going to be looking at from section 7A, it's going to have us go through and do, it's called the midpoint rule, which is basically the same thing we did earlier back in section 5.1, I mean. So call this the midpoint rule. And what it says is the nth midpoint approximation of the integral from a up to b of f of x dx is the following thing. We have midpoint approximation is equal to delta x, then it's times f, the function f evaluated at c1 plus function f evaluated at c2, plus so forth and so on until you get the function f evaluated at cn. And in this expression here, each of those delta x, that is interval length divided by n, that is our delta x. And the cj, this will equal a plus j minus a half times the delta x. And that right there is the midpoint of interval cj minus 1 up to cj. So this is our midpoint rule. And then we got a problem where they're going to have us calculate the trapezoid rule and the midpoint rule for a certain expression. So we're going to go through and do that. And then the last thing from this section is something called Simpson's rule. So, which is just basically another way of figuring out the area under a curve. So we want to calculate T6 and M6 for the integral of 1 up to 4 of square root of x dx. So let's use the, let's go up here and get our trapezoid rule so we can see exactly what we're doing and what plugs in where. So let's do the T6 first. So T6 wants us to figure out the trapezoid rule. So we'll say, all right, T6. All right, so this will be 1/2. Delta x is going to be the upper limit of the integral 4 minus the lower limit of the integral 1. And that's all divided by the number of things we're breaking this into, which in this particular case, we're going to break this into 6 pieces. And then we have y0, y1, 2 times y2, 2 times yn minus 1, etc. So if we think about this, it's y0, y1, y2. We could use the this function of a plus j delta x, but let's think a little bit about what this really is kind of representing. So we have our interval from 1 up to 4. So say, okay, if I have my interval from 1 up to 4, and I want to break 1 up to 4, so that would be 1 up to 2, 2 up to 3, 3 up to 4. If I want to break this into 6 pieces, if I look at this delta x here, if we kind of consider that delta x, 4 minus 1 is 3. 3 divided by 6 is 1/2. So this, everything right in here, this delta x term is 1/2. So what that means is if I look at the interval 1 up to 4, if I break it into halves, so 1 up to 1.5, 2 up to 2.5, 2.5 to 3, 3 up to 3.5, and 3.5 up to 4. This should give me 6 intervals. 1, 2, 3, 4, 5, 6. So instead of using the full, trying to use this a plus j delta x to generate every single one of these values, It's easier in this particular case, since you're only breaking up into 6 intervals, kind of look at it and figure out what your delta x is. Once you know your delta x, you kind of know how the intervals are going to break up. And then all we have to do is to get these y sub zeros, we just evaluate the function at those points. So this will be square root of the first bar, which is 1, plus we get 2 times the function evaluated at the next number. So we got y0 is just the function evaluated at the starting point 1. It's 2 times the next one, which would be square root of 1.5, plus 2 times the next one, which would be square root of 2, plus 2 times the next one, which would be square root of 2.5, plus 2 times the next one, which would be square root of 3, plus 2 times the next one, which is square root of 3.5. And then we're at the final one here, which doesn't have an extra 2 on it. So that one will just be plus square root of 4. And now we just need to put that all into our calculator to figure out what that ends up equaling. And if I type it in correctly, I should get this is about equal. The book says it's about equal to 4.661488. So we'll just say if I plug that in my calculator, that is what that would turn into. So we calculated T6 using this method. Let me bring my thing here, the way that what we use to kind of break this up. When we go to find M6, so we'll say, all right, let's look for M6, the midpoint approximation of this. So M6 says it's going to be delta x, which said, okay, delta x is a half. And then we could plug in everything into this kind of complicated formula. It's the function evaluated at each of these c values. Each of these c values is a plus j minus a half delta x. And then, as we get those, we total them up. This doesn't have any of those little extra numbers, like the trapezoid had extra 2's in here. This just is the function evaluated at numbers. And these little CJ's, these are the midpoints of the intervals. So what that's kind of saying is if I can figure out the midpoints of each of these intervals, so if I can figure out of the 6 blocks, what's the midpoint at each of these places here, what value does the midpoint of each of these segments fall at, I can just apply the function, which is a square root function. I can just take the square root of those values and total them up and multiply them by half, and that would be our midpoint approximation. So 1 up to 1.5, that would be square root of 1.25. Plus 1.5 up to 2, the midpoint would be square root of 1.75. When we go from 2 up to 2.5, that's 2.25 falls in the midpoint. 2.5 up to 3, that would be square root of 2.75. 3 up to 3.5, 3.25. And then for the final one, 3.5 up to 4, that would be square root of 3.75. And if we put that into our calculator, we're going to get that's about 4.669245. That would be our midpoint approximation. If these have a more complicated, maybe it's like, I don't know, maybe it's 12 bars and you can't really tell where things are going to be, then you do have to use the equation, and you plug A as 1, and then you'd let J start at 1, then it would become 2, then 3. You'd subtract it by half and multiply it by the delta x, and you can then take the square root of that mess. But it's just sometimes if you can kind of use the geometry and say, well, if we're breaking this up into 6 parts, I can figure out what those 6 parts are, and then for the trapezoid rule, I have exactly what I need. Then for the midpoint approximation, if I already know where the little 6 segments would fall, I can figure out what's the midpoint of each of those segments, and I can just get at the y value kind of just from doing geometry rather than having to let the equation tell me how to find it. So that is a bit about the trapezoidal and the midpoint approximation. The last thing we got from here, we're going to ignore all the error-bound stuff from this section. They don't ask that really on the AP test. So the final thing we need to do from this section is something called Simpson's rule. And this is just another way of approximating the area under the curve. So what this tries to do is Simpson's rule. They use Sn for Simpson's rule. They try to take kind of weight the trapezoidal approximation for 1/3 of Simpson's rule, and then weight the midpoint approximation for 2/3 of Simpson's rule. And so Simpson's rule is kind of formed by a trapezoidal and a midpoint approximation, where the midpoint approximation is weighted slightly more than the trapezoidal approximation. And this basically is, they do this to try to make the approximation more accurate, is kind of the idea behind this method. So what Simpson's rule says is for n an even value, so you can only find like S4, S6, S8. For Simpson's rule, you can't find S7. You can't break it up into an odd number of segments. We say the nth approximation of, we'll say integral from a up to b of f of x dx is, and they give us this thing here. So Simpson's rule, Sn equals 1/3 times delta x. And there's going to be kind of a weird pattern where the y0 doesn't get counted anything. So you kind of have a pattern like the trapezoid rule. We had y0 is by itself, then we had 2 as numbers in front of all the in-between stuff, and then the last one was back to yn. For Simpson's rule, y0 is by itself. You get a 4 for y1, then it's a 2 for y2, then it's a 4 for y3, and it continues on being 4, 2, 4, 2, 4. Eventually, you get a 2 for yn minus 2, plus a 4 for yn minus 1, plus, and then you get to the end, and that's just yn itself. So instead of having all 2 patterns, you have kind of this alternating. It starts with the 4, and it goes 4, 2, 4, 2, 4, 2. It'll stop with the 4. And then the starting number and the stopping number here don't get any little numbers in front of them. And then in this expression here, delta x is still what we expect it to be. Delta x is still the interval length divided by the number of segments. And we have the function f is evaluated at a plus j delta x. So what this means is if you can figure out how many segments this is supposed to be broken into, you can use this right here as what your yj value is supposed to be. So to wrap this up, this will be our last example from this section. So let's say example, we want to find S8. 8 is an even number, so it is even, so we can use Simpson's rule to find S8. 4, they give us the integral of 2 up to 4 square root of 1 plus x cubed dx. So again, since we're breaking this into 8 segments, let's kind of figure out delta x, and let's see if we can just kind of geometrically figure out where the first segment start should be, the first segment stop, the second segment stop, etc. Let's see if we can just kind of figure this out. For delta x, we're going to get it's 4 minus 2, so that's the interval length, divided into the 8 segments we're going to break it up into. 4 minus 8 is 2, so this is 2/8. So this is going to be 2/8 is 1/4. So, okay, we're counting up by fourths, so let me get a different little color here. So we'll say, all right, our interval is going to start over here at 2. It's going to stop at 4. We're breaking it up into 8 pieces. And each of the bars will have a width of 1/4. So we'll say, all right, this is going to be 2 up to 2.25, 2.25 up to 2.5, 2.5 up to 2.75, that up to 3. I'm going to need to space my bar a little bit further because the way I'm writing these need a little bit more room. So we'll have 3 up to 3.25. Then we'll have 3.5. Then out here we'll have 3.75. So we're using the delta x. We're starting at the lowest number. We're stopping at the upper number of our integration. So this tells me the inputs that will be plugging these values into the x in the function that the integral is taking place of. We'll be using 2, then 2.25, 2.5, and we can see that there's 1, 2, 3, 4, 5, 6, 7, 8 intervals, which matches up with what we expect there. So let's go and do Simpson's rule. So S8 for this problem, we got a 1/3 out front. We multiply it by delta x, which is, delta x in this situation is a 1/4. Then it's going to be the y sub 0, which will be this function evaluated at 2. So we get, okay, we're going to write this all out. So we'll have square root of 1 plus 2 cubed. That's the y sub 0. Then the y1 term here has a 4 in front of it. So we get, all right, plus 4 times the square root of 1 plus 2.25 cubed. So I'm plugging it into here. Plus now the next number is 2. It's 2 times 1 plus 2.5 cubed. Get another 4, so we're making the 4, 2, 4, 2 pattern. It's 4 times the square root of, we're up to 1 plus 2.75 cubed. Back to a 2, so plus 2 times square root of 1 plus, see, next one up is 3, so that'd be 3 cubed. Plus 4 times the square root of 1 plus 3.25 cubed. Plus 2 times square root of 1 plus 3.5 cubed. Plus, we get another 4 square root of 1 plus 3.75 cubed. And then the final one doesn't have a 4 or 2. It's just the square root of the last number, 1 plus 4 cubed. So we get that, this one doesn't have any number in front, then it's 4, 2, 4, 2, 4, 2, 4. And then the last one doesn't have anything in front of it. So that'll give us Simpson's rule. If we type that all into a calculator, take a little bit to do, this will give us approximately 10.74159. And that's basically how you set up for Simpson's rule. Again, you could say like, A is the starting number 2, so we could say that this was 2, and then plus J is 1 to start out, 1, and delta x was a 4th. And so we could say, all right, that's 2 plus 1. 2 plus 1 times a 4th is 2 plus 1/4, which would be 2.25. Then J would become 2, so that'd be 2 plus a half, which is 2.5. Then J is 3, so it's 2 plus 3/4, which is 2.75. So you could use the formula to generate those numbers, but since we know the interval length, we could find the delta x. Once we knew the delta x was a 4th, we could kind of see how the interval from 2 up to 4 was going to be broken up, where you do little 4th steps each time. So we could break that up into our eight segments, and then we can use these numbers here as what we plugged in for x. Then we just make the 4, 2, 4, 2, 4 pattern with it. And that's basically what we needed from section 7.8. So we'll stop this video there, and that'll do it.